All right, so two things that we're going to go over before I start going over and helping people. So first off is, well, I guess three things. So first, this is going to be the last session in which I go around and help people today. That doesn't mean that I'm going to stop helping you. It just means that like if you want to, um, if you need to meet with me for help, you'll need to message me on Discord or send me an email. Because I'm going to be busy on the next couple lectures getting you prepared for the final exam. I plan on doing some practice, a bunch of practice problems. There's some various exams from other universities I'm a fan of, but also doing things like looking at Tokyo University entrance exams. They typically have like in previous, half a decade ago, they would at least list one data structure problem on their entrance exams for their computer science graduate program. So it was a good, and I thought those were good things to look at because they were fairly, in-depth questions to look at. Okay. The next thing to do. So just be sure to turn things in about that. I'll also be going over the last homework today, but before we do that, I want to go over I want to check the final exam stuff. Final exam. So final exam schedule, Temple, spring 2023. This is the way I find it, just like everybody else, which is that I go over here and boom, there it is. Okay, those sound like the right dates for this year. Okay. So this year we're listed as a common final. Yes, we are. So final exam on campus Friday, May 5th. So your final exam is next week. Ooh la la, right? It's that's spooky, I guess. Okay, so but I think that's good. Typically what I've found, so here's why. Typically what I found is that most of my students, typically we don't hold the final exam on that Friday. Typically we're more like over here when we on the May 9th, which is later. But you say, oh, that's good, right? No, it means you're already wiped out from all the other finals you had to take. So at least this one will be earlier. I found that a lot of students are just simply exhausted when they get to my final and overwhelmed, and they don't study as much as they needed to, or the review session we go over this over the next 2 days isn't as fresh. So as for where it will be, I'll send that out in an announcement. I believe we've secured a common room for all of 2168 in the in Circ. Now there should be chargers. I'm going to check out the room, but I believe in Circ there should be chargers underneath each of the tables, so you shouldn't have to worry about that. If Murphy's Law does happen to strike you, I will help you work around that. I'll try my best to, accommodate you without necessarily penalizing you with, I don't want you to get sent into, I don't want you to start panicking and have your exam result, suffer as a result. So just be sure to, just please, for technical difficulties, understand that Murphy's Law says that whatever can go wrong will go wrong. So, so that's what we're going to accommodate, or sorry, that's what we're going to plan for. So again, final exam will be 3:30 to 5:30 on 5/5. We will tell you when that is. If you have a time conflict for that exam, please let me know. If you have more than two exams, if you have more than two exams on the same day, please let me know. I'll be happy to proctor you over Zoom or something like that. Okay. Otherwise, my plan for the exam is to enable you to use, idle and idle will be, me and the other professors will be going around the room, making sure that you are using only the resources that you're allowed to use, e.g. no going on Google to find the problems, please. Because they do the best to make them, good. I'm going to be writing that final exam in the next couple days. So yeah. Okay. Any questions about that?
You said in the past that the first five questions could be not open node, closed node. Could you
I'll double check on
elaborate?
that. I
Okay,
need to
thank you.
double check what my rules are from last semester. Okay.
Thanks.
Okay. Yeah, but that's correct. The first five questions I might make them closed note because I use those for data collection and purposes. So just kind of seeing student, not like you personally, but like overall kind of thing.
And one more question.
Mhm.
Would you say it's more focused on the second half of the class, graphs and trees, than first?
Say that's accurate. There's more of an emphasis on the later on the later half of the semesters. Linked list will definitely make an appearance, but not like in the same. But you'll more be using. But you're going to be expected to use the built-in linked list kind of appearance there. Okay, as opposed to writing a linked list from scratch. Okay, other questions? It's about half theory and half practice. Yes. What?
There's no group section.
No, there's no group section on it. You're on your own. All right. So I will send out more details, but I promise you that the exam, that content-wise, my exam review will be quite thorough. Okay. So with that said, let's go ahead and take a look at the last assignment, which is, I know that some of you, if you've taken a look at it, you're probably like, so how do I go from A to B? Like, how do I go from here, where I am, to a solution? Okay. So for those of you who haven't, so you're going to download this and you're going to find, oh, that's a very short assignment. So solve problem 79 on Euler. This is a graph problem to size. So we're going to sit down and figure out what the node is and an edge. What do we have to do? So basically, remember, graphs are all about relationships. So we're trying to figure out what are the things that have relationships and what are the relationships between them. So we can do this in any model, but what we're going to be relying on is something called the in-degree of a node. The in-degree of a node is as follows. Given a node, the in-degree is the number of edges that are coming into it. So this node over here, node A, has an in-degree of 3. Node B over here has an in-degree of 2. There's also like an out degree. So let's go, actually. There's also such a thing as out degree over here. A over here now has an out degree of 1, right? So in degree is the number of things leading into you. Out degree is the number of things that are the edges that lead to other nodes. But really, all we care about here is the in degree for this problem. So the number of edges that lead into a node. Otherwise, it's so there is a built-in function in Jung to use that. And otherwise, it shouldn't be too bad for your other one. So let's see. Project 79 in Euler. It says a common security method used for using online banking is to ask the user for 3 random characters from passcode. Although, while this is it says it's common, but I've never seen it. So, it's saying over here that if the user's passcode is 531278, then it might ask them for the second character, the third character, and the fifth character. So 317. If I were to ask it for the first, the fifth, and the sixth, it would be 578, because that would be the first, the fifth, and the sixth. So we're just asking, like, what index do you want? Index being, but you don't have to care about the indexes here because this is not necessarily a point of the problem. You just gotta understand that what we've got over here is that we've got a file for a single password. Okay. A file for a single password that contains 50 of these button presses, these logins. So given that the three characters are always asked in order, analyze the file so as to determine the shortest possible secret passcode of an unknown length. So here, what we're seeing is that we know that the 3 was pressed, the 1 was pressed, and the 9 was pressed, but we don't know the full password. All these are the same password. So these are different like subsections of the same password. 6, 8, and 0 was pressed. 1, 8, and 0, 9, 6, 6, 9, and 0 was pressed. The only thing we know, though, is that these button presses were in index order, not the first. So we don't, like, for instance, if 3 was the very first button press, though, sorry, 3 was the very first index, like 3 is the very first thing to appear in the password. That doesn't mean that 1 is at index 1 and 9 is at index 2. This means that 3 is at some starting point, and then 1 is further along, somewhere unknown, further along in the password, and 9 is further along that. All we can know is that in the numerical password that we have, the 3 comes before the 1, and the 1 comes before the 9. Make sense? So with that, we actually have enough to build our relationships for this. So in this case, our nodes are the numbers that we push, right? And the relationship is which one comes before the next one. So 3 comes before 1, which comes before 9. Let's go ahead and just draw that with our nodes and our edges, right? 3, 1, and 9. Let me go ahead and maybe change the color to something a bit brighter, since I'm drawing on. Okay. 3, 1, 9. Is that better? Yeah. Okay. Now the next line says 6, 8, and 0. So 6, 8, 0. Draw those on. Okay. And now we go to the next line. We see a 1, 8, and 0. We don't draw a new line or anything like this. Those 1, 8, and 0 already exist in our graph. So we go 1, we know that comes before an 8, and the 8 comes before 0. That's already in there, right? 6 comes before 9, and the 9 comes before 0. Go ahead and redraw that slightly so I'm not overwriting. 6, 9, and 0. Next, we've got 1, 2, 9. So we've got a new thing over here. So let's go ahead and, let's see, 6, 2. Yeah, let's go ahead and put the 2 over here. Yeah. So 2 over here. You have a 1, a 2, and a 9. And then the next one is a 6, a 2, and a 0. Yeah, it gets non-planar, which is a graph term. So a planar graph is a graph that basically you can draw it and none of the edges are going to crisscross each other. There's a more formalized definition, but honestly, that's like the human definition we can use. That makes it really easy for us to kind of figure out, oh, it's planar. There's properties that just, now there's, again, the point of there being a mathematical property is that there's a bunch of ways to draw a graph. You can draw pretty much a lot of graphs that are planar in a non-planar fashion, you know, because you might be like me and bad at drawing stuff. But here we can see that we've got that. So, and then finally, we've got the last number we need to add, 7, 6, and then 2. So, and 6, 8, then 6, 8, 9, 3, 1, 8. I'm just going through and finding what I need to find now. So what we do is that we keep reading this. So your process for this problem is that you read through this file and build up this graph, okay, until you go through all of them and you build up all the edges that you can, okay? And I'm just going to grab some of the ones I needed, which were 7 that I know I need from experience. 7, 3, 1, 7, 3, 6. Okay, there we go. So the reason for this is that what we've drawn here is what I've called a DAG, a directed acyclic graph. Directed, meaning we've got directed edges. Graph, it's got node and edges. So it's a directed graph. The acyclic means that there's just no cycles in it, meaning that if we choose any point to start with, and follow the edges, we'll end up at some sync location, someplace where there's no cycle. Okay. So directed acyclic graphs have a thing you can do to them, which is called topological ordering, which if you watch my lecture videos, that's kind of the last topic about that. That's used for like saying, okay, what are the what prerequisites do I need before I do other classes? What things need to be imported? What libraries need to be imported in order to import other libraries? Dependency charts like that. What directions have to be filled before we do other ones. Now, what we're going to do is that we're going to do a variation of something called Kahn's algorithm to solve this problem. Kahn's algorithm is you can follow Kahn's algorithm exactly. And when I say Kahn's algorithm, I'm talking about K-A-H-N, Kahn's algorithm. It's an old one, but it checks out. Kahn's algorithm for topological sorting. That's Geeks for Geeks. I like Wikipedia. So you can find it here. And it goes over, it says, hey, it was published in 1962. It's got pseudocode over here with lists and sets, which makes it, and that makes it fairly easy. But you can use a variation of this. And the variation is and the way it works is very simple. Check all the nodes, find the one, and find any of them that have an in degree of 0. Now, because this is a math problem that needs to be checked, there's only going to be one ordering. So every time you do this algorithm, there's only going to be one thing with an in degree of 0. So we check all the nodes, which one has an in degree of 0? In other words, which one has no nodes, no arrows coming into it? That's 7. 7 has no arrows coming into it. So here's what makes Kahn's algorithm so nice. We're going to write down 7. So I'm going to change my color. We're going to write down 7 or not. Excuse me. We are going to do this, draw. We are going to write down 7 over here, and we're going to delete the 7. And when we delete the 7, we're also going to delete the edges that come out of 7 because it makes sense. There's no need for them. So, okay. And then we continue until there's nothing left. So we delete 3 next. So we check all the nodes, which has an which has an in degree of 0. Let's see. Happened over here, 6. So which has an in degree of 0? 3 has an in degree of 0. So we remove that. And also I'm working off of incomplete data right now. Like I didn't do the entire thing. So just keep in mind that if I have to stop, it's because I didn't read the entire file. So next we look at everything else that has an in degree. So notice that 7, 6, and 1 both have an in degree of 0 now. It should be unambiguous, but if I had read the full file, I would have found 3 comes before 1, which comes before 6. So we could have done that edge right there. If you read the entire file, they'll all show up. So again, we delete 1, all of its outgoing edges go away too. And we continue on until there's no nodes remaining. So step 1, read the file, use these numbers. Each number represents a node, and each pair of numbers represents an edge. 3 going to 1, and then 1 going to 9. You could also put in 3 goes to 9 as well, because logically that follows, but there's no need. You get what I'm saying? You go through all the full file of this stuff, and you build it up, and then you run Kahn's algorithm, which is what I just did there. And your output should be a list or a string, which of what buttons to press. If you want to check your password, if you want to check that you got the right answer, all you have to do is create an account on Project Euler, which I highly recommend because the problems there are great for practicing kind of the higher end math skills and learning some weird stuff. And then after that, you'll be able to get a pop-up, you'll get a box over here that you'll be able to plug the answer into, and it will tell you whether it's right or wrong. Okay, but I mean, it should go like 7-3 something. So if you got that, it's probably going to be right. Now, if you're using Jung, which I bet a lot of you will because Java, okay, then one of the Jung's peculiarities is that when you build a node, you know, I can build 3 and 1, but when I build this, I need to build the edge and give that a name as well. I highly recommend using integers as your nodes and strings as your edges. What string am I going to use here? I'm going to call this edge the 3, 1. Why? That's a great question. And the reason is because if I go back down, if I go through this file again and get to this 3, 1, okay, in Jung, what we have is the add edge command. That's how you build it, with add edge. And add edge takes in 3 things. It takes in the edge A, edge B, and the name. And the thing is that this is a, you know, simple graph, meaning that there's no more than one edge between any 2 nodes. But, you know, checking if an edge already exists, that's another check. So you'd either have to do that, or you can do what I do, which is when you add the edge, you between 2 nodes that already exist, use the same name. In which case it's going to go, oh, that edge already exists, so I'm just going to skip it. Otherwise, if you try to add a different edge, like over a second edge, it will crash. So again, just long story short, if you missed all that, when you're building everything in Jung, use integers for that, for your nodes, and strings for your edges, and name your string basically the numbers, you know, the string of one of the first number plus the string of the second number concatenated with each other, you know? So 3 and 1 should be edge 3, 1. That will make it easier. Yeah, and I'm sure there's a similar thing that goes on with NetworkX, but it's Python, and Python's very easy, very flexible and easy. Overall, this problem isn't too bad. Once you get, the hardest part is building the graph, I think. And again, the Khan's algorithm over here of how it goes through it, okay? It says here we're going to get our empty list, which has the topological sorting. Unlike, you know, other sorting algorithms, it's not going to go from smallest to biggest. It's going to go from the order we parse things. The set of all nodes with no incoming edges. So what we do is, well, it's not empty. So obviously you'll just have to start it by figuring out what it is. This is why I say you'll modify it. I'd modify it to say like, hey, look at while the graph is not empty, look at the graph to find which node has the no incoming edges. Add that output to your edge. And then it says for each node with an edge, remove that edge. Honestly, we can skip this kind of step where we've gone through where it says, hey, we need to go through and remove all the edges. Because a lot of graph libraries, if you remove the node, it's going to remove all the edges that are associated with that node as well, right? So check your graph algorithm. But I know in the case of Jung, if you delete the node, it's going to delete all the edges you want to delete as well, and keep all the edges you want to keep. And then you just simply keep everything else in the graph. Then you keep everything else. Yes, you're kind of destroying your graph as you do it, but hey, that's the entire point of the problem. If you wanted to keep the graph, we could do something else. It says if the solution is a DAG, a directed acyclic graph, a solution will be contained, although the solution will not necessarily be unique. This solution is unique based on this last thing, especially that shortest possible passcode. What that essentially says to us is that we know that there isn't going to be duplicate numbers. There's not going to be duplicate numbers in this. Otherwise, it would get much long. If that was the case, it would get much longer. So that's why we're able to assume make the assumptions we want for this. All right. The only other thing I have to say before I move on to helping people is speaking with one of the professors who teaches 3223. They said that, again, I think I've said this last time around, that they recommend if you need to take 3223 for your degree, which most data science students and most data science students and most computer science and every computer science student used to do, but not necessarily ISMT. So if you need to take 3223, take it as soon as possible after this class, because this class, because your memory will be as fresh as possible, essentially. So you don't have to review all the stuff in this class. If you do need a review, my YouTube channel isn't going anywhere. So keep that in mind. That's my only suggestion. And again, a lot of companies, they love to grab questions from this class and 3223. So those are the kind of subjects you might want to study. All right, so start recording.